Ever wondered how AI models like GPT or BERT actually understand language? It's not magic. It's a blend of mathematical precision, clever architecture, and decades of research. Today, we're diving deep into the inner workings of modern AI, unpacking the technical heart of transformer models, the role of attention mechanisms, and the latest breakthroughs pushing the field forward. Let's get technical. Let's start with the foundation, the transformer architecture. Introduced in 2017 by Vaswani et al. Inattention is all you need. This model revolutionized NLP by replacing recurrent structures with self-attention mechanisms. But why does this matter? Unlike RNNs, which process text sequentially, transformers analyze entire sequences in parallel, drastically improving efficiency. How does this work? At the core is the self-attention mechanism. Imagine a sentence like, "The cat sat on the mat." Each word looks at every other word to determine relevance. This is calculated using three matrices: queries, keys, and values. The dot product of queries and keys determines attention scores, which are then softmax normalized to create weights. These weights are applied to values, producing a context-aware representation of each word. It's like giving each word a vote on its meaning based on the entire sentence. Now let's break down the math. For a given token, the attention output is a weighted sum of value vectors. Attention QKV equals softmax, QKT slash square root DKV. Here d, k is the dimension of the key vectors, and the scaling factor square root dk prevents vanishing gradients. But transformers don't stop there. They use multi-head attention, splitting the query, key, and value matrices into multiple heads. Each head captures different relationships, and their outputs are concatenated and linearly transformed. This allows the model to learn diverse patterns, from syntax to semantics, simultaneously. This architecture isn't just theoretical. Take BERT, which uses bidirectional transformers to pre-train on massive text corpora. By masking random words and predicting them, BERT learns contextual embeddings that outperform previous models. But here's the kicker. BERT's success hinges on its position embeddings, which encode word order. Unlike RNNs, which inherently capture sequence, transformers rely on these embeddings to maintain temporal awareness. This is a critical distinction. Without them, the model would treat sentences as unordered bags of words. Of course, transformers aren't flawless. Their quadratic complexity in sequence length, ON2, limits scalability. Enter linear attention and sparse attention models, which reduce computational overhead. For example, the longformer uses sliding windows to focus on local contexts, while reformer leverages locality-sensitive hashing to compress attention. These innovations enable processing longer texts without sacrificing performance. Looking ahead, research is pushing boundaries. Models like GPT-4 and LaMDA now handle multimodal inputs, blending text, images, and code. Meanwhile, efficient transformers like T5 and MBART are optimizing for real-world deployment. But the real frontier: neural architecture search and meta-learning to automate model design. The future isn't just about bigger models, it's about smarter, more adaptable systems. Thanks for watching. If you want to explore the math behind attention mechanisms, or dive into the code of a transformer model, hit the link in the description. Don't forget to like, subscribe, and join the conversation in the comments. What breakthroughs excite you most? Let's keep pushing the limits of AI together. Stay curious, stay technical, and keep learning.